identification. But of course, in my talk, I will try to discuss about different deep learning techniques for, yeah, it may, of course, my main goal is person identification or person identification only, but person identification, definitely we need text information. So if there is a text available, if a text is available, definitely we can extract the text information and recognize him or who is that guy, something like that. So yeah, that's the way my work, my talk focus in this, session. So new application is actually instead of Salford, Manchester. So yeah, just I joined on Monday. So it's a new job for me and new task for me. Okay, in this task, I will try to cover three kinds of, three categories. Number one, how we can use handwritten text analysis for person identification. That's number one. And the same way, how we can use scene text or text in the video or scene images for person identification. So maybe you can see in marathon images or sports images. So where you can see in marathon you can see bib number, and in sports also we can see jersey number, and there will be a name also in sports video. So yes, my job is to detect such text information in the video and marathon, and finally we should recognize the text to identify the person. So that's the whole story here. And another one actually personality behavior, that means in personality traits identification. So can we identify the person behavior with the text analysis? Not only text analysis, maybe multimodal approach. Let us use an image information as well as a text information to identify the person behavior. So that will be the last topic. So I just classified into three categories. Of course, here. So what you have to focus here. Okay. Anyway, see, my talk goes like this. So I will try to discuss the recent challenges. Okay, these are all the new challenges which we assign to different students of a PhD, masters, project like that. So of course, I am not in machine learning guy or a deep learning guy. I will try to discuss in this session how we can use deep learning technique to solve a new challenge. So I'll just try to explain what is the motivation and why did you propose this kind of deep learning. So in that way, I'll try to bring deep learning topics in this session, okay, in this talk. So, but most important is you need to focus on what is the problem here, what is the application here, and what is the challenge here, and how we can confirm that this problem is really challenging. That is most important. So maybe anybody can choose this problem. These are all new challenges, so nobody has done work on these challenges. Of course, so only few guys are working on these challenges, and we are the one publishing few papers on these topics. These are all totally open issues and new challenges. So probably I think you will get in some information that. So yeah, this is a new challenge or this is a new area. So yeah, which you can continue for your research topic or any publications. So that is the way you need to utilize my talk, and you need to expect something from my talk. Okay. So yeah, since I'm not a deep learning guy, I may not explain in details of architecture and layers, how it works and how it forms. So those things I may not cover, but I will try to cover. So what is the motivation to bring deep learning here? So that means you will get a one picture here. Okay, there is a challenge here. Okay, how we can use deep learning, how we can propose a deep learning. There are so many deep learning techniques now. You take any paper now, everywhere deep learning is there. Without deep learning, you cannot publish any papers now. So this is a trend now. So yes, because of that, we also started using deep learning techniques to solve our problem. So otherwise, we cannot publish any papers. We cannot survive in this competition. So yeah, we know very well that why do you propose this, or why do you introduce a deep learning? So we know very well that. So that those things I will discuss in this talk. Okay, this is the first one. So EUA net. Okay, a new edge attention based unit for nationality identification. Look at the problem here. Okay, just title is enough to understand how we can use this information for nationality identification. So nationality identification means, so nowadays you can see, yeah, English handwritten by different country people. So you have to write an English text, okay? You have to take an English text written by different countries. So maybe India, Nepal, Pakistan, China, okay, Palestine, Sri Lanka, like this, of course. So now the question is it possible to identify the nationality by just analyzing handwritten text information? That is a big question mark here. So we cannot find any work on this problem. Only we people published one or two papers on this topic. It is really challenging because it is a, first of all, it is a handwritten text. It is not just a normal text or printed text. So you know very well that if it is handwritten text, there will be lots of any variations in writing, because we call actually freestyle writing, and there won't be any constraints. So pen can be different, ink can be different, paper can be different, and of course even sometimes we write in a two sides also, is single side and double side. So yeah, these are the main issues. Of course, if you use an old paper and aged paper, yeah, these are all so many issues when it comes to handwritten text. So apart from on top of these additional challenges, so how we can identify when person or in the nationality? That means we can identify this is the text written by this is the guy and this is the country and a guy representing this country. So how it is possible? So this is the problem here, and of course this is a really open challenge now. So yes, one can think of solving this problem, or one can think of taking this problem as a your research topic. So definitely, absolutely, it will be fine. It will be very good. So what is the idea here? What is the idea behind to solve the problem? See, look at Indian nature, how we people write English, how Chinese people write in English, how Pakistan, that is in Arabic countries, people write in English. So look at in the Chinese actually. So when you look at the Chinese, of course we usually take samples um, written by the person who has a practice of using his own mother tongue. It is not something like a migrated guy. We don't take samples from a migrated guy. So I'm coming here. So of course, in UK there won't be any different language, it's English only. But of course, I was in Malaysia. Okay, I'm a migrated guy. So assume that I know how to write Malay. Okay, so that should not be. So of course, you have to take a samples from the person who has a practice of his mother tongue. His mother tongue. Okay, so that is a minimum criteria. That is the minimum condition is required for this work to collect a number of samples. Okay. Now look at the Chinese guy. You know how the Chinese guy writes Chinese? It is always in boxes. Okay, there will be one box, and within that there will be another box. Within that there will be another box. So that means you have a practice of writing in a boxes here. So boxes in the sense what horizontal and vertical strokes will be there. There won't be cursive. But look at the Indian scenario here. Look at all languages in India, including Kannada, Tamil, Malayalam, Hindi, Gujarati, any language in India. So definitely more or less those languages are actually cursive in nature. So we usually write cursive things, right? Not actually vertical and horizontal strokes. But look at the Chinese guy. Chinese guy always write in the boxes here. That means he has a practice of writing in boxes. That means you can expect a more straightness, horizontal and vertical straightness in the case of Chinese guy. If Chinese guy write English text, we can expect a more straightness, more horizontal and vertical straightness. But in if English written by Indian guy, we can expect a more cursive things in the text written by Indian guy. So this is the idea behind here. That's true also. That's true also. But how we can extract this kind of an observation? So that is what the challenging here. That is what actually the contribution here. Okay. Of course, we are trying to look at the title here, a new edge attention based unit. So we are trying to explore unit also and edge based attention. That means when you are trying to introduce something, that means you are trying to modify unit so that it will extract the edge information properly. See, if you want to solve this problem, what is very important? Edges are very important. You take any handwritten text, even not only handwritten text, even take any scene analysis, image processing. You take any image processing without edge, we cannot understand anything in the image. Nobody can propose any method without edge information. Of course, first of all, if there are no edges in the image, we cannot see what is there in the image. We cannot even understand what is there in the image. It is something like if there are no edges, it looks like just in a blank or homogeneous region. So of course, if there is a homogeneous and a dark and in a plain region, what we can understand? Nothing can be understand. Okay, nothing can be noticed in the image. So obviously, edges are more prominent in the case of image processing. You take any image processing, any approach, more all methods, all models and all people focus on edge information only. So in case of handwritten also, edges are most important. Why? Because we write in strokes, right? So we write what is the style of writing. So obviously the style, everything depends on edges only. If you are able to extract edge information accurately and properly, yes, more or less the problem is solved. So problem will be solved. So that is true in the case of handwritten text and even printed text. Any text, any text. If you take any text, edges are more prominent here. So edges definitely give a lot of information for us. So here also we try to exploit this kind of features. So see as I mentioned here, if there is a Chinese and Indians, definitely yes, we can differentiate with the help of straightness and cursiveness. Okay, in case in Chinese handwritten text, definitely we can expect a more straightness and Indian text. So while Indian text, definitely we can expect a cursive, more cursiveness here. See, in the same way, we can expect a different variations and different observations with respect to different countries. Okay, so this is what idea here. So of course, our approach is actually we are trying to bring in a unit here. Why unit? That's the question mark here. So unit is, as you know very well, that I think you have been listening to deep learning. Deep learning, probably I think you people are, you people know very well, better than me. Okay, you people know better than me. So anyway, unit is, of course, you take any segmentation, especially medical domain. Most of the paper, most of the time, we see unit, and of course, there are so many variants in the unit. So not just in a basic and classical model of any unit. So there will be lots of variants and variations to variations of any unit now. So here, of course, we did not use a different total new model or in a different new unit here. We just used in a basic unit only, and we try to add something to that so that unit can extract clearly edge features here. See here, see the problem of an extracting edge feature. You look at the text information here. So look at even in samples also. See when you write properly within a force, yes, we can see some edge information. But anyway, we don't put any constraints here. We don't have any conditions. We don't have any assumptions here. So yes, guy can write. Okay, yeah, he can write in anything and he can write in any way, and we don't ask him to write after this post this speed. Yeah, we don't put any constraints. We don't have any constraints here. So definitely yes. Yeah, definitely yes. He can use any pen and he can use any force and any speed here. So in this situation, so how we can extract edge information? So if edge is prominent, yes, we know that. If edge is available, yes, it's easy to extract the information. If edge is not visible and there is a blur, there is a noise, and there is a just low contrast edges, then it is very difficult now. So that is what. So our focus is try to extract edge information. If we extract a proper edge information, then our problem will be solved. So this is actually a simple approach in handwritten text analysis and yeah, document analysis also. So we also did the same thing, but only the change here is, okay, we just proposed a unit, and yes, in addition to that, we just added edge attention, you know, module or edge attention component to unit. That's a simple contribution here. Okay. Yeah, this is a simple diagram here. So this is what handwritten text. So usually we extract the words here and we binarize the word, and finally we design edge attention unit here. So how this contribution work? That is the most interesting part here, and that is what a contribution also. And finally, this is very simple. We just used a CNN classifier. So that means you just see when you look at this diagram, easily we can understand and notice that. So we are trying to extract the features by proposing edge attention based unit. So that means we are trying to use unit for feature extraction, and of course we are trying to add attention module to extract a prominent edge information in the image. So okay, that's a simple contribution here. So what is that architecture? I think, see, motivation, anyway, I've already mentioned the motivation. Of course, what is the motivation for proposing any unit? So why unit segments properly? You take any segmentation, there will be unit. So you take anything, especially medical domain. Yeah, oh my God. So in the medical domain, yeah, people are exploring, like anything, exploring unit like anything. Okay, so to solve the problem. So yeah, we believe that unit is something like, of course, it's a combination of, encoding and decoding and, encoder and decoder, right? So okay, upsampling and downsampling. So definitely yes, it tries to extract the information based on semantics. It is not just separating the reason. So it will try to separate the reason based on the semantic. So that means it is not just classifying the pixels, it will classify based on the meaning. Probably maybe we can say the context information. So again, what do you mean by context here? So probably yes, if you want to define a context, you need to know what is foreground background here. So maybe yeah, we can assume here. So background, it will, to decide what is the edge information, it will try to consider it will try to consider background of any edge information. So that means, see, in the text, look at the text information, look at the handwritten text, even normal text information, even scene text information. Look at inside text. Let us say O is there, inside O, outside O, okay, and boundary of the character. It is very clear. See, it is very clear. If you talk to any document analysis guy or document guy, yeah, these are all very simple and basic observations. So when you look at a character here, so what happens? Inside there will be hole, inside there will be background. So that background will have any uniform values. Of course, not exactly 000 or 1111. There will be small variations, but yes, we can see uniform values. Okay, that's the background. And similarly, look at the boundary point here. Boundary will have an always in high values. And similarly, outside boundary. So outside boundary, because of the background influence, we cannot expect uniform values here. So of course, we cannot even predict what kind of values are. Okay, so because of the influence of a background here. Okay, so that means look at the scenario here. Outside boundary, we cannot predict what kind of a neighbor values. Inside boundary, we can predict what kind of values here. Boundary pixels will have in high values here. See, when you analyze this kind of an information, easily we can define some kind of a context and relationship here. Okay, so look at the background of an outside character, background of inside character. So background of it's also same background. It's not something different background. It's the same background, but inside character, yes, it's the same background, but will have uniform values. Outside background, outside character, the background of an outside character will have different values. Though it is the same background, but inside will have a uniform value, outside will have unexpected, unpredictable values. See, you can easily define some relationship here. That is what the meaning of a context here. In between, there will be a text information. In between, there will be a dominant and edges will be there. Look at the edges also. Look at the pixels of edges. Do you think in all pixels in the edge, all pixels of an edges will have the same information or uniform information, or pixels of edges vary? You have to check that one. If there is an influence of a background, then we can expect a small variations. And more than that, when you write even handwritten also, even a printed also, look at the stroke width information. Look at the stroke width. What I'm saying is stroke width here. So that is thickness of the stroke, the thickness of the stroke. So look at your handwritten, look at your printed also, look at now the text here, whatever you are seeing the text here. The stroke width remains constant for the whole character. See, these are all dominant features to represent handwritten text information. And of course, if you are able to extract this kind of an observation, this kind of an features, we can solve any problem. We can solve any problem. That is what all we people do. We were in document analysis. We always look at any edge information, how edges are changing, changes. Okay, how edges are changing. So when you change the problem and you change the data set, when you change the samples. So our idea, our observation is always focus on edge information here. Okay, see, I was trying to tell I was trying to give an information, trying to tell what do you mean by context here, how we can define a context here. Okay, so what do you mean by context? This is what the context here. Look at the boundary pixels will have a high value. Inside boundary will have low values. Outside boundary will have unpredictable values. This is what the context. This is what we say high level features. Of course, we just don't talk in a number of values on mean, median, mode, something like that. So we'll try to find some relationship between. We define the relationship. Okay, outside on the boundary, inside boundary. This is what the meaning of a context feature. So that means what I'm saying here, what I'm trying to say here, unit extract this kind of features to separate reason of interest. Okay, that means it will try to extract a semantic information. Based on the semantic information, it will decide this reason is something different, this reason is something different, this reason is something different. Of course, that's what a unit, but we in our work we need we need edge information. So we try to add something to get not just reason of interest. Because we want edge information. So for that we had something else to get edge information from the reason of interest. That's the whole story of any unit here. Okay. This is, I think you know very well, this is unit. So look at what are the changes we made to architecture here. So what are the changes we did here? So this is the residual and gated convolutional, residual block and gated convolutional block. Yeah, just we are adding these two blocks, okay, as additional constraint to unit. Of course, just that a unit gives a reason of interest. Okay, that is the job of unit here. So from the reason of interest, we need to extract edge information here. So how we can extract edge information? For that, we introduced two residual and blocks and gated convolution block. So residual blocks, you know very well that it will take in original information to decide what it is, and gated convolution block, it is something like a filter. Okay, it will try to filter out because there is a reason now, reason segmented by the unit now. So unit gives in some reason now. Within the reason, there are so many edges now. How we can extract edges? This combination, residual and gated convolution, it is exactly work like a, behave like a filter. Okay. So of course we need an high pass filters. We'll try to remove the low values and we'll keep only high values here. So that means here, what is the contribution here? The contribution is very simple. So okay, the combination of residual and gated convolution block, okay, with basic edge, basic unit model. That's the simple contribution here. Okay, what we can understand here. Okay, I'm not explaining how this works and what is this architecture. So those things, because they're all basic models. So we're not doing anything to the basic model here. We are just adding extra things here. Of course, residual block and gated convolution block. Okay, we're just adding these two things to basic model here. Okay, so that means what you can understand here. Yes, everyone knows that unit is good for image segmentation, reason segmentation. But if you want to extract edge information, specific edge information, yes, this is the one way of adding some constraints, adding some filters to extract edge information. That's all. So that's the motivation. That's the thing you need to learn from this talk. Okay. So of course, yeah. Once you understand that, oh, okay, there is a basic unit now. Oh, okay, these people added residual indicated convolution block now. Now you can think of your own constraint, your own filter to add this one. Now, of course, unit is combined with so many even vision transformer also. Now the trend is they try to combine different basic models now. Basic models now. Okay, unit with vision transformer. Okay, different attention models with yes, so many things. Even now, I think now at present, and everyone talking language model now. Okay, transformer is also gone now. So now everyone is talking about a language model now. Okay, so earlier just it was a deep learning. Now it is not just deep learning now. So we just went forward now. So we are moving towards language model now. I don't know what will happen in future. So anyway, so in this topic, you need to understand that okay, we proposed unit for edge segmentation, and of course, in addition to that, so they have just included residual and gated convolution block to filter edges from the segmented region of interest. Okay, that's all. That's a simple contribution here. There are samples now, qualitative results. I won't give so many details in this talk. Just I'll try to show architecture to get some idea what kind of an architecture we have proposed, and finally, yes, how it gives in the results. Okay, so input, yeah, this is EU, this is the result of the combination. Look at the edge information. So definitely, what you have to observe here, for every samples here, samples of different country, yes, you can see edge information. That is what our target. So when you run this modified unit, okay, we should get edge information. That is our target. Yes, we got it. So though there are so many variations in the input image, yes, this is the background is different, this background is different, this background is different, this background is different. Look at now. See, I tell you, I ask you a simple question. What is edge here? When you change in the background color sometimes, okay, then it should work. Okay. So that means background is white now and foreground is actually black. And maybe for another image, background can be dark and foreground can be white. Still, it should work. That's what actually job of any unit and deep learning now. So that means deep learning will try to extract the changes from one pixel to another pixel. So not like in high value, low value. If you look at the high value, low value, it will not work. Because see, when you change the background, suddenly yes, foreground becomes a high value and the background becomes a low value. So anything can happen. So when you change background and foreground, okay. So that means our algorithm should not depend on values now. So our algorithm should depend on gradient. Actually, we define a gradient. Actually, the gradient means the way you change the pixel. Okay, the rate of change of the pixel values. Okay, not just changing the value. What rate it is changing the value? In what way it is changing the value? So if you extract that kind of an information, yes, it will work for any background. Okay. So that's what the advantage of a deep learning. When you propose a deep learning model, automatically it extracts any meaningful information. Okay. Yeah, this other one. New parallel attention model for multiple license plate number recognition. Okay, so look at the problem here. Now this is actually car identification or maybe vehicle identification. How we can identify the vehicle? See here, look at the title here. We try to use, try to propose a parallel attention model for multiple license plate number recognition. What is the problem here? So usually you take any topic, I will try to highlight what is the challenge here, and then I will try to highlight what kind of a contribution to solve the problem. Okay, those two things will be I will made clear those two things. Okay. Okay, what is the problem? Multiple license plate number recognition. So that means if one image contains too many vehicles, of course, Indian scenario, if you look at Indian scenario, it will be really too complex problem. Because here probably you can see only one kind of an vehicle, one type of an vehicles here. But in look at an Indian scenario, there will be a motorbike, there will be a truck, there will be a bus, and there will be a two-wheeler, three-wheeler, auto. So many things will be there. So when single image or single video will have different types of a vehicle, then how you can detect and recognize the license plate number? See, when you have too many vehicles, obvious problem is occlusion. Number one, because we cannot see properly license plate number. Okay, and number two, see defocusing problem. What do you mean by defocusing problem? See, when you have multiple vehicles, your camera focus, of course, not just one vehicle. How we can focus on multiple vehicles in one image? That means now we can focus in one camera. That is impossible. So obviously, it is actually your focus will be scattered. So when focus will be scattered, yes, we call this one as a defocusing problem. So that means if there is a focus, then you can expect a good information. We can expect a high contrast information. When focus is not good, what happens? Yes, you cannot expect high values here. The problem here is when you have too many vehicles in one image. So let us say this license plate will have a high contrast, another license plate will have a low contrast, another license plate will have something else, another maybe blur, another one maybe noisy. Like this, multiple adverse effect can be expected when you have multiple vehicles in one image. This is really challenging problem. So far, we have solved the problem when image contains a single image. When image contains too many vehicles, today I'm telling you, okay, whatever I am talking, these are all actually not Indian scenario, not with respect to Indian scenario. If you look at Indian scenario, it will be too complex problem. But so far, whatever we have done, we targeted only normal images and a normal data set, not really very complex data set. Maybe yes, one can think of an Indian scenario. So how see, especially look at in a traffic signal, right? So these motorbike, two-wheelers, definitely they will, park like anything. It's not something like any one lane. In abroad, what happens now? If there is a traffic jam or something, there will be a clear lanes lines. You cannot even imagine that. You just if you look at those vehicles, you just the whole scene look like a showroom. How in showroom clearly in the park and cars line by line and one by one, right? Exactly the same picture can be seen when there is a traffic jam abroad here, but even in Malaysia also. But in India, no, 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 no. So if there is a traffic, no, yeah, suddenly two-wheeler comes here and he will park in front of the car, and the other two-wheeler comes here. Yes, see, this scenario is too complex actually. So how we can detect, recognize license plate number in with respect to Indian scenario? Okay, this is really an interesting problem. But now, see, now I'm trying to tell you what do you mean by parallel attention model? That is a problem. Okay, that's a problem. So of course, application is we are trying to use the license plate number for chasing the vehicle or tracing the vehicle or maybe identifying illegal parking or anything, or maybe theft vehicle, or maybe yeah, some people I think sometimes they change a license plate on the plate number also, and they do some we call actually attacking. That means they will try to hide license plate number by putting something, by adding something to that. So these are all actually forgery or maybe attack. Those are all different issues. Anyway, I won't talk into those issues here. So now here, just you need to focus on there will be too many vehicles. When you have too many vehicles, it will be defocusing problem and occlusion problem, blurring problem because camera changes, right? When camera changes, definitely there will be a blur also. We can expect a blur also, low contrast, high contrast. And the problem here is in one image you can expect we can have too many things here, not just one thing. Okay, so that means multiple factors can be seen in one image, multiple adverse factors, not adverse factors in one image. So if it is, yeah, if one image contains so many things, then how we can develop an algorithm? Because we don't know. In this corner something is different. This corner is something different. In middle something is different. So here will be something different. So when something is unexpected, something is unpredictable in one image, it is not so easy. If whole image has uniform things, then it will be very easy for us to solve the problem. So in that way, this problem is very complex. Okay. Now, how did you? Okay, we proposed here parallel attention model. See, look at the word parallel attention model. So why we can introduce parallel attention model? That is what you need to understand here. Other things are easy for you. We can go through our paper also, or maybe you can just Google it. You will get a lot of information. Okay. So now parallel attention. Why we brought parallel attention model? Okay. See, look at license plate number here. License plate number. Each character is actually independent. It is not something like in a text. If there is a text, maybe restaurant, hotel, there is a meaning. Okay, you take any word, name, not name. Name doesn't have a meaning here. But maybe yes, look at any in a hotel, restaurant, or in a building. You take any word, so there will be a meaning. Okay, for the word. So you take any word, there will be meaning to that, meaning to that. But look at the license plate number. There is no meaning, right? Each character is independent. So 7, 6 is a numeral, and suddenly we can see some alphabets. And what is the relationship here? How we can connect these characters? How we can say these in all these characters give one meaning? How we can say all these characters are coherent, correlate and have some correlation? How? That is not possible. That is what advantage of bringing parallel attention model. Okay, that's the motivation here. So that means since each character license plate is independent here, 7 is independent, 6 is independent, 1 is independent, 5 is independent. Nobody knows in a 7, 6, 1, 5 gives in some meaning. Nobody knows that one. Of course, there is no meaning to that. It is just number. Okay, RG, it is independent character. R is independent. G is independent now. So since every character is independent here, now we can bring in a parallel attention model here. That means we are trying to process every character simultaneously. Okay, so in that way, yes, this work is something different compared to different from an existing methods here. So of course, attention. Why do you bring an attention here? Again, the same thing what we discussed in the previous topic. So that means, of course, as I mentioned, this problem is very, very complex. We can expect a low contrast, high contrast, and even blur also, noise also, so many things now. Of course, how we can solve this problem? Definitely attention model is very important here. What do you mean by attention? Attention means the word look at the attention, it will draw your attention. So that means you are trying to highlight something which can draw your attention. That's the meaning of an attention here. So there will be specific conditions to extract, prominent features, or especially, of course, we can see any edge features only. Okay. So parallel attention model for multiple license plate number recognition. So look at the architecture here. It's very simple architecture. So for us, this is not a totally different architecture. We used an existing architecture only, but we just change to parallel attention model. Okay. Now look at see the yeah, these are description features extracted block of features with name sequences passed through transformer unit, which generates feature matrix, and attention mechanism is then applied to generate separate features for corresponding each target sequence. Okay, next it is passed through fully that's the last one. So okay, how we can classify it, how we can take a decision, that is all depends on in a fully connected layer. That's the last step, and in between there will be a feature extraction and transformer. Okay, so that is most important here. Anyway, I will not show in our paper. Maybe yes, if you want more details we can see details in the paper. Anyway, yeah, if I start showing the paper and explaining the things in the paper, then probably it will take too much time. So anyway, let me just complete without showing the draft. These are all latest work and recent work. Okay, I think I've already explained this one. So this observation motivates to propose this deep parallel attention model. It's fine. And of course, another thing is when you go for a parallel attention model, definitely we can achieve simple results here. Look at now. So yeah, even if it is one thing you have to remember, when you develop an algorithm for solving complex problem, the same model should work for even simple problem also. That means what I'm saying here, I kept telling you, okay, this problem is very challenging. Why? Because in one image you can expect multiple vehicles. Because of the multiple vehicles, this problem is different and very complex and very challenging, right? So when you develop an algorithm for solving complex problem, yes, the same algorithm should work for simple. That means when image contains a single vehicle also, high contrast image also, it should work. That is the way. So some people, yeah, I've seen in so many works also, yeah, when they develop algorithm for solving yeah, complex images or issues, when you give any simple image, it will not work. Nobody accept this kind of things. Nobody appreciate this one. Okay, so this is the thing. And yeah, of course, the most challenging part is when you compare to other deep learning techniques, especially scene text recognition detection. See, most of the time we propose deep learning model for scene text detection recognition by looking at meaning of the text information. So we'll try to target extracting meaning of the text. Based on the meaning of the text, we'll try to say this is a text information, this is a non-text information. But those models can license plate number. Why? Because license plate number will not give any meaning to you. So definitely, yes, it is really challenging. That means what? You cannot use any existing models here. You need to do something so that it will work. What is that something? That should be the contribution. Okay. Yeah. Another one. See, this is number reduction in day and night. See, now I'm trying to increase the complexity of the problem now. Not only multiple vehicles, now day and night images now. Definitely, yes, it is not so easy. Of course, you take an Indian images, Indian license plate numbers. So look at the night. What is the challenge when you take night images or when you include night images as a sample or input in your data? Definitely, yes, night image.
Hello, sir. Hello, sir. Unmute ಮಾಡಿ sir audio.
It was disconnected. Huh?
ಹೌದು ಸರ್. ಒಂದು ಫ್ಯೂ
Oh,
ಮಿನಿಟ್ಸ್ ಅಷ್ಟೇ. ಸರಿ ಆಯ್ತು.
oh, okay, okay. Now we should be all right. Okay, right. Oh, sorry, it was disconnected. Anyway, so this is the third challenge now. So Gaussian kernels-based network for multiple license plate number reduction. So this is something different from the previous one now. So earlier one just multiple vehicles in one image. Now we are adding one more complexity here, night images now. When you have a night images, of course, obviously, yes, the problem becomes too complex. Okay, because when look at the night images, the traffic light will be there, and headlight will be there. That means you can see illumination effect here. When there is a headlight, we cannot see license plate number because of the two headlights. So and illumination effect. So license plate license plate number between two headlights may not be visible. Okay. So this is the more challenging problem. But how we can solve the problem? That's what interesting idea I'm trying to share here. Look at it. This is what an idea. You need to understand. I mean, these things. See, without idea, you cannot propose. Even if you propose, nobody will appreciate. Nobody will, accept your work. Idea is most important. So you need to understand the first challenge. Once you know the challenge, then you have to bring some idea to solve the challenge. That is most important. Other things easy. Other things are easy. So nowadays, I think if you just ask your students, or obviously you will bring in a deep learning model or any model, but yes, you need to justify it. Why? How it works? What is the observation? What is the idea behind? Simply, we cannot bring in a model and give input and output. That should not be. That is nobody accepting that kind of work now. So anyway, so that is not my job to explain now. So now, how we can solve the problem? Gaussian kernels. Look at the word Gaussian kernels. Network, which is network for multiple. Okay, that means here what is very important. The word Gaussian kernel now. See, why we brought in Gaussian kernel? That is where I'm trying to solve the problem. So what is our problem? Night, day, and multiple values. That means in one image you can expect multiple adverse effect now. So that means there will be many variations in one image now. So how we can handle this problem? Yes. Look at your character or even text also. You just count the number of text pixels. Okay. When you count the number of text pixels, so definitely you can expect a Gaussian, right? So Gaussian curve, in the sense what? Yeah, maybe most of the pixels will have some uniform value, and only few pixels will have a high value, only few pixels will have a low value. This is very true. It is not in a new version. This is very, very true. You take any text information, this is true. This is a very, very common observation. All document analysis people use this kind of an observation. Okay, this is not something different, but how we use this observation to solve our problem. That is what an idea here. That is what actually our thinking and our research here. See, I know that there are so many problems, there are so many variations in one image. So what we did here, it is very simple. We try to define a different Gaussian kernels here. So that means let us say this character has a low contrast. Yes, for this, we know this character definitely will look at the distribution of the pixels which represent definitely Gaussian distribution. We know that. We know that. Okay. So definitely, yes, it will represent a Gaussian distribution. So that means what? We try to define different Gaussian kernels. So if there is a low contrast, yes, there will be another kernel here. High contrast, there will be another kernel here. So that means what we did actually, we proposed multiple Gaussian kernels here to handle multiple problems in the image. That's the beauty of the work, nothing else. Other things are very simple. Okay, so yeah, there will be. I think we proposed in this work. I think just we proposed the three Gaussian kernels, not too many, but yes, now we can extend that one. So look at the challenge now. If the problem is too challenging, very complex, then you go for a multiple kernels, not just in one kernel, not just in a three kernels. Of course, for every kernel, there should be justification. Simply, we cannot bring so many kernels here. So for every kernel, what is the role of this kernel? What is the role of a kernel 2, kernel 3? And like this, you have to have a justification. Yeah, maybe one kernel for low contrast, another kernel for Gaussian kernel for high contrast, another one. Like this, probably we can introduce many Gaussian kernels here. But what is very important? This is very important. Text. Look at the text. Look at the character. Especially distribution of the pixels will represent Gaussian distribution. That is what the idea here. That means you are always looking for a Gaussian distribution. That means when you find a Gaussian distribution, definitely you can say there is a text, there is a character here. But look at the non-text information. Maybe there is an object. There is something, yeah, non-text. Yeah, background can have any objects, any kind of any shape, any objects now. So can we expect a Gaussian distribution? No. Maybe, of course, there will be one or two objects who may probably overlap within a Gaussian distribution. Yes, that will be there. That's an exceptional case. You cannot say that our algorithm works, give an 100% result. That is impossible. You cannot solve a problem completely. Yeah, there will be always limitation. There will be some limitation. There will be some constraints. There will be assumptions will be there. Yes, I'm not telling that point, but definitely yes. You look at the text information. Definitely it represents a Gaussian distribution. So your job is to look for a Gaussian distribution. Okay, with the different kernels. That's how the problem is solved now. So what we did actually, initially we proposed in Gaussian kernels to get in some region of interest. This is actually density map, we call it density map. So that means wherever less security is there, we can expect in a high density map here. It is something like in a bright information. Bright information is a region of interest. So wherever you see in a bright patch, yeah, probably you can say it's a region of interest. And the region of interest should be input for next step. Again, we use Gaussian kernels only. Again, one more time, again use the Gaussian kernels to find something within region of interest. That's all. See, that means idea is propose Gaussian kernels because we know that every Gaussian kernel represents a text information. Whatever may be the text nature, whatever may be the background, whatever may be the complex, you just look for Gaussian distribution. That look for reason which satisfying Gaussian distribution. That's all. Okay, anyway, I've already explained this motivation, so it's fine. Yeah, just these are all very known things. These are all actually not new things actually. Dilated convolution and DCNN is very known things, and even one MCNN. Yeah, these are all known network, not in a different network. Okay, next. Yeah, this is a architecture. Probably you can understand. It's very, very simple. Just we are feeding a Gaussian kernels to the network. Nothing else. All just sampling, up sampling and down sampling. Okay, look at now how it works now. It's a detection part. So multiple vehicles it works, even single vehicle works, day works, night works. Why? Because our kernels are very the way we propose the kernels actually solving our problem. Okay, another one. Probably I should go fast. I don't know. So what is the time now? So this is what another problem. What is this one? Watermark. Yeah, now I'm trying to explain, text reduction in video. Okay. So definitely, of course, so how video text is different from, normal scene text image. Okay. So video text will have, okay, when look at the, maybe assume that you're watching a video, news video, or you're watching a news, maybe definitely we can see in a subtitles in the video. Okay, there'll be subtitles. We call actually subtitles are as caption text here. So another text, yeah, in the image, yeah, which should be part of the image, maybe building name, it's a part of the image, as we call actually scene text information. Another one, so watermark, sometimes you can see watermark calls. This is where this problem is actually different now. So we have already solved problem of caption and scene text detection recognition. We have solved this problem, but when we include a watermark text, so do you think it is easy to solve the problem, easy to classify, easy to detect and recognize the text information when we include a watermark? No, because now watermark, see why this problem is very challenging, because watermark text has its own properties and its own nature. Similarly, caption has its own nature and its own properties now, or characteristics now. Syntax has its own nature and its own characteristics now. So now exactly the same as you just go back and think of in the same previous problem. When single image will have multiple things, definitely the problem can become complex now. It's the same thing. Only thing is different text here. So previous one, different license plate. Here, the text now. So watermark has a difference. So now your job is to classify three different types of text now. Okay. So for that, again, we proposed in a unit 3 plus. Okay. So look at now, actually full skip connection. That's what we call as full scale skip connection approach. See, this is what you need to do. Earlier, I have shown in one unit. So for the basic unit, we just added Gaussian, what is not Gaussian, the residual and gate convolution blocks to extract edge information. Here, same unit only, but yes, we try to add something to that. So there is a basic model. For that, we are trying to add something here. What is something? Yeah, we just very simple intra connections and interconnection. That's all the difference here. That's what they defined this net with a different name, unit 3 plus. Unit is there, 3 plus. They added 3 plus. Why? Because of intra connection and interconnections here. So these are interconnections, these are intra connections. Okay. See, it is not just a skip line. So skip lines between two, um, downsampling and upsampling. This is one. And now within upsampling, yes, there will be interconnections. Yeah, this is what we call actually modified unit now. So because of these additional things, we are trying to extract, we are trying to segment all three types of text, though these text in one image, present in one image. That is the whole beauty of the work here. Okay, that is where the contribution comes. That is where our problem is different here. Okay, so look at now. So this is a one architecture, and this is actually we call actually end-to-end architecture. So what do you mean by end-to-end architecture? This is also very interesting in concept. So end-to-end architecture means, yes, once you give input, you should get an output. You should not know what is happening in between. So maybe I think you might have worded end-to-end encryption. So WhatsApp, I think when you open WhatsApp, you can see there will be a word end-to-end encryption. So that means you should not know what is happening in between. Once you give an input, yes, you should expect only output. That is what an end-to-end meaning, but it is not so easy to implement end-to-end meaning. So because End-to-end meaning is, see, let us take in text detection, text recognition. There are two stages now. So in this case, actually segmentation and detection. Okay, in this work, actually there are two stages: segmentation and detection. There are two stages here. See, if you want to prove it is an end-to-end model, this is what you need to remember. Okay, so yeah, probably you can read, you can see many models define end-to-end model in many papers explain end-to-end model. But what do you mean by end-to-end model? Yes, you need to understand. See, in this case, maybe take a simple case, detection and recognition. Okay, detection is one stage, recognition is another stage now. So how we can say this is end-to-end model? Okay, there are two stages here. So we should not feel that these two stages are different. We should not feel that there is a one model for detection, one model for recognition. No, it should be integrated. It should be unified model. You should not you should it is not something like, okay, you take output of first module and give input to second model. No, that should not be. Okay, once you start training, yes, training should be common, data sets should be common, and extraction should be common, and finally output should be the final output. There won't be anything in between. Okay, but how we can define, what is the definition here? I tell you, see, you take in detection here, output. Okay, after detection you will go to the recognition. Fine. Now interesting point is, we have to use recognition result to improve detection. It is something like a feedback mechanism. Feedback. So when you justify there is a feedback mechanism, then only we can justify end-to-end model. So in this case, let us say recognition. Okay, you recognize the text information. Now we can cross check whether recognition result is accurate, correct, or wrong. If you think that something is wrong here, then you come back to detection now. Come back to detection, improve the detection now. So once you improve the detection, again you go back to recognition now. It is something like in a cycle, okay, feedback mechanism. So indirectly what we are doing, okay, recognition should help detection, detection should help recognition. Mutual sharing should be there. Okay, so if we don't define a mutual sharing, then we cannot justify it as an end-to-end model. So in okay, let us take a simple example here. Recognition, recognizing a non-text information. Let us say non-text. Okay, so when you recognize non-text, definitely you will not get any results. You will get some garbage. Once you get a garbage, you come back now. Okay, detection. What is happening? In case of detection, detection step detected non-text as a text here. That's a false positive. Okay, when you send false positive as input to recognition, recognition result gives garbage. So that means we are coming back now. Okay, recognition result is actually garbage. Now you are coming back and you try to eliminate false positive in detection stage now. So you are trying to improve detection. That means you are talking. There is a mutual exchange between detection and recognition here, sharing. Okay, there is something sometimes we call actually communication between detection and recognition. If here your model can communicate between two stages, okay, or three stages, but of course I've never seen any end-to-end model for three stages. Most of the time end-to-end model so far I've seen only two stages. So maybe enhancement, recognition, or detection and recognition, like this only. But I never seen enhancement, detection, recognition, prediction like that. I've never seen. Of course, that's what actually our target also. So one of our students is actually working on. So how, see, when you have multiple stages, how we can define end-to-end model? Because you have to ensure that there will be communication between all these four stages. If it is a two stage, it is easy to define communication. But when you have four stages, how we can define a communication? How we can communicate? Okay, suddenly prediction should communicate with the recognition, and prediction should communicate with the detection. Prediction should communicate with the enhancement. Similarly, detection should communicate with the recognition, enhancement. Yeah, it's not just one to one. It's many to many. Okay, it is a very interesting topic. It's of course can solve any problem here with you if you think properly. So here, yeah, that's what the meaning here. So here the problem is watermark. So when you have a watermark text, the problem will be totally different now. It is not same as old problem of caption and text information. Okay, how we solved here? Just a simple thing. We have proposed a unit, modified unit. Okay, this is the detection thing. Sample results, and next one. So new language independent. What is this? I cannot see. Okay, new language independent deep scene and for syntax reduction and styles transfer in social media images. See, this is again something different. See, look at the problem here. Language independent, syntax reduction, and style transfer in social media images. What do you mean by style transfer here? That is actually our target. Okay, so when you give a text information, when you give an image containing a text information, what is our job? Detect the text information and then transfer its style. Style transfer is something another work now. That means there is a, let us say there are two kinds of a text here. One is the target text, another one input text now. So we can exchange style. What is the style? Maybe foreground. Okay, foreground can be interchange here. Okay, interchange with the target text, target and input. When you give a both target and input, you can interchange the style here. So that is the style transfer. This is again the combination of a deduction and text. Style transfer is something new in this work. Okay, and most important thing is social media images. You need to understand. So when you use in social media images, yes, it will be totally different from normal images here. And another point is language independent. Your method should work for any language, not just one language. Okay, not just English. You should for Kannada also, Tamil also. It's language independent. And even style transfer also, not just in one language. Okay, English to style transfer can be done from English to Kannada also, Kannada to English also, that is possible. Okay, but more than that, what is very important here? Social media images. In this way, our problem is totally different here. So what I mean by social media images? What is the okay? When you use the social media images, what will happen compared to normal images? Definitely, it will be different. See, look at your WhatsApp image. So when you download from the WhatsApp image, do you think it will have the same quality as original image? No, we will lose the quality. But in our case, what we do, we just upload and download. Okay, we just upload and download with the different social media platform, not just in not just in one platform like in WhatsApp, Facebook, social media, Instagram, Twitter. We use the different social media here. That means assume that same image is passing through different social media now. Okay, you are okay. So now you uploaded, downloaded from using WhatsApp. Again, same image uploaded and downloaded using another social media platform. That means when you take upload and download it from the from different social media platform, then you look at image quality. What happens? Because every social media has its own mechanisms to store the data. Whatever you upload, it will not store as it is because it's impossible. Also, you are uploading video. Of course, you are uploading a high resolution video. Do you think the Facebook guy will save as it is? No, that is impossible. If he keeps saving, then he cannot bring any memory here. He cannot have a sufficient memory for that. Okay, he cannot buy something in a very large memory. That's impossible. So what they do, every social media platform will have its own mechanism to compress the data. Okay, so that means what is happening when you upload and download, when you do upload and download with a different platform, so definitely it will reflect on the image content. Okay, so because of different mechanism of storing and saving or compression, definitely you can see the effect on content of the images now. So again, I am trying to define the problem, actually multiple problem, multiple challenges here. So same image will have a different quality now. Earlier also I was telling you multiple adverse factors. Here also multiple adverse factors, but not in terms of some other things, in terms of quality now. Okay, so that is where the problem is challenging. Okay, so how we can solve the problem? Here also we proposed, I think unit plus, definitely efficient unit plus here. Okay, efficient unit plus. Yeah, maybe I'll show you probably the next one. So see, approaches like this: input and see. This is in government of India. We have extracted the text information, and this is what transferring. Okay, input and transfer now. How we can transfer? This is the look at the output now. Okay, that means English to Hindi. So that's what style transfer. So this is a simple result. Okay, now see, look at now we have recognized and even transfer the style. This is one more problem. So a new deep CNN for 3D text localization in the wild through shadow removal. See, look at now. Now we are talking about a 3D text localization, not 2D. So this problem again is totally different now. So far I was talking about in a 2D, but now I'm talking in a 3D now. So definitely 3D text is different. 3D text is really complex compared to 2D text now. So detecting, recognizing 2D text is easy because it's a 2D. But when you have a 3D, what is the specialty of a 3D here? When you have a 3D, then you will have a depth information now. Because of the depth information, what we people do will design in the characters in different way. There will be design in the background also. There will be design in the character also. That means you can expect in a decorated characters here. So when you have a decorated characters, you can expect in a multiple sized characters here, multiple aspect ratio. Okay, multiple characters with a multiple aspect ratio. So you look at a 2D, usually you will have in the same size of the text. That means an aspect ratio. Look at the size of the character and the height and width of the character. So it will be almost same in one line. But in case of in a 3D, yes, no, it's not. We cannot expect uniform character, uniform sized characters here because you have in a 3D extra depth information. Because of the depth, you are trying to decorate the character here. You write in different design the character. Okay, you write in the character. So how we can solve the problem? So it's again text localization or text reduction and text conversion. Now, how we can solve the problem? So one simple way is, of course, there will be shadow also because when there is a 3D, yes, we can expect a shadow also. So of course, even if you when you capture a 3D in orthogonal direction, okay, head-on direction, then it will be 2D only. If you capture a 3D text in different angle, then we can see some effect here. Okay, so that means what is the effect? Probably you can expect a shadow, you can expect perspective distortion, and probably you may lose some shape also. And we can add one more deformable shape. What do you mean by deformable? Shape a little bit changes. Of course, it will not lose any complete shape. Yeah, there will be a small, slight changes in the shape. That's a deformable. So deformable, perspective, and one more shadow. Okay, this is the problem. So for this, of course, we proposed it's another thing you have to understand here. Sometimes we use only deep learning model because deep learning model can do everything. Okay, feature extraction also classification also it can do everything now. Sometimes we use the combination of an handcrafted features and deep learning model. So in this work, we proposed yes gradient vector flow. It's in a classifying a text and shadow pixels. So using some feature extraction, we extract some features to classify 2D and 3D, and then we localize the text using deep learning model. So you need to understand here what is the difference between using deep learning model and a combination of extracted features and model and a deep learning model. Yeah, there will be a debate. This is not any easy to explain and easy to justify. But yes, group of people argue this one is correct, this one is a good. Some group argue this one is a good. So some people argue that, especially machine learning and deep learning model argue that unified model, deep learning model is the best one. That is the best way to solve the problem. Because deep learning means when you are applying a deep learning, you should not use any pre-processing and post-processing. That is the advantage of deep learning model. So if you are doing in a conventional way, pre-processing, then solving the problem at the end to improve the result, you bring post-processing. Then it is a conventional approach. There's nothing wrong, nothing new here. So if you use these things, then now at present nobody accept because if you want to show what is the advantage of a deep learning model, yes, you need to avoid pre-processing, post-processing. Then only people accept your model is good. Otherwise, yes, even if you propose a beautiful and fantastic model, again, if you say our model depends on success of pre-processing and post-processing, then nobody believe and nobody accept the things. Okay, this is the one kind of an argument. Another kind of an argument is like this. If you just use a deep learning model for solving the problem, then you will lose generalization. So that means it will limit to specific things. We cannot extend, we cannot expand, we cannot apply on different things. Generalization is the problem if you use just a deep learning model, because of course you know very well the deep learning model depends on number of samples. If you change number of samples, if you change any parameters, and if you change yes, something in application, definitely yes, you cannot, definitely yes, performance goes down. You cannot see a 90% accuracy for different things. That is impossible. So in order to balance generalization and accuracy, now sometimes we use in a combination of handcrafted features and deep learning model. Because when you use any handcraft features and deep learning model, yes, we can expect a little bit, more generalization ability. Because features, whatever you extract based on the observation, that will work for anything. Okay, that will feature extraction. Always we extract a feature based on some observation. That observation is common for any problem, any input, not any problem, any application and any input here, any samples here, observation. So because our feature extraction depends on the observation, yes, it will work for different samples, even less number of samples, even if you increase the number of samples, even if you change the data set, it will work. So after extracting such features, then you try to use deep learning. So then it makes some sense. Okay. So that is what the idea here. So of course here what we need actually shadow removal. See how we can solve the problem. One way is develop an algorithm which can work for 3D, 2D. That is one way. Another way is try to remove shadow information. Once you remove shadow information, it will be as good as a 2D now. So 2D, yes, we have already developed so many methods for 2D. So now you just remove shadow. Now when you remove shadow, it becomes in a 2D now. Yes, your problem is solved now. So in this work, we used actually shadow removal. Okay, how we can remove any shadow? See, this is simple again. How shadow is different from an actual text? Definitely look at the shadow information. Shadow will have uniform value and low values will be there. Contrast is not very high shadow compared to boundary of the text. So that was a simple observation to separate shadow pixels and text pixels. Okay, here efficient unit. So we defined this as the efficient unit because we use a mobile network here. So this is see efficient. We use this a combination of mobile network and unit. That is the way you need to bring in a contribution here. We are not changing the basic model here. That's what everyone do now. If you change the basic model, then you can define your own model. So how the people are defining a unit to this one, maybe you can define a S net or Z net or Y net, who knows? You can define different way if you really change the architecture. Okay, you are not good in changing architecture because that's actually job of machine learning people. So we are not machine learning people. So generally, what we do, we try to analyze a different architecture, and finally we'll try to do some combinations. Okay, this combination is actually because I want to prove that we want to prove that it is efficient. Okay, we want to prove that our method is efficient, so we brought the combination of we brought a mobile net and we combine with a unit now, so it becomes efficient unit. Okay, simple result now. See, look at now we are trying to remove shadow information. So if you remove shadow, the tool. That's a simple idea. So another one again, soft set based MSCR end-to-end system for occluded syntax detection, recognition, and prediction. Look at now. See, so far I was just talking in detection recognition. Now we are trying to solve an occlusion problem. This is very common. So when there is a text, okay, so definitely it will be obscured by different obstacles, right? So assume that vehicle is moving, suddenly the vehicle is moving, yes, it will block text information. Or you are moving in front of the text, then yes, you are blocking the text information. So this is very common. This is very common. Occlusion is very, very common. So can you predict text information? Okay, yes, that means, and if you get if you take any incomplete text, maybe there is a word which misses that misses in a few characters. So is it possible to predict? Of course, definitely it is possible now because NLP is very powerful. So if you bring NLP concept, yes, we can easily predict what should be the correct word. So that is what this work we are trying to combine with natural language processing concepts, NLP concepts here. That is where this work is something good and beautiful. Okay. So look at now the problem is text detection, recognition, and prediction. We need to predict the text information here. So we detect the text information, recognize the text information. After recognition, yes, we need to predict it. So that means something recognition is just you are recognizing A, B, C. Okay, if there is a, there is a B, but it won't say what is that word. But prediction means you are trying to predict the whole word. Even if word misses few characters, yes, it will predict what should be the right word. That's a prediction. Detection, you are just localizing, that means in extracting the text information. Recognition, you are recognizing it is A or B or C, but prediction means you will try to get a complete word, even the word misses few characters. So that's the challenging here. And here the approach is soft set based MSCR, end-to-end system. Look at now. Soft set, I think it is a kind of fuzzy only. It's not something different. So MSCR concept. Everyone knows an MSCR concept. It's a well-known concept. It is very popular. So if you use MSCR, automatically you can get connected components. Okay. Maybe let us say each character is one component. So to extract each component, each character as a component, you can apply MSCR. That's a well-known inbuilt function. But this MSCR, how it MSCR works? We know because we're all image processing people. We know how MSCR works. MSCR try to fix a boundary based on the values of the pixel. Okay, based on the values of the pixel. That means MSCR has many stages here. Every stage has one threshold. So that means every stage it will define a one threshold. So to define MSCR, to obtain a components using MSCR, you need to fix many thresholds here. Of course, it's all automatic. It's not something in the manual. It's all automatic. But we observe when MSCR works, when MSCR doesn't work. Of course, MSCR works when character is single character will have same contrast and uniform things. But that is not true in case of an occlusion. You are missing something, part of the game, part of the character. So yes, MSCR, normal MSCR will not work. And some part of it is actually affected by blur. Some part is affected by noise. Some part affected by background. So when character gets affected by different things, definitely what happens, you cannot expect uniform pixels for the whole character. So MSCR will not work, especially in our case. So we brought softnet now. So to stabilize, the thresholds, okay, to fix stable thresholds, we just introduced something like a soft set, which is same as fuzzy only. Okay, that is what new contribution here. So there is a MSCR. Yes, we don't want to use a conventional MSCR. We just added soft set to decide a threshold here. So we don't want to don't want to use MSCR threshold. We just added soft set to decide what is the threshold. Concept is same. Steps are same. Just when you are deciding a threshold, you try to use soft set concept. That's one contribution. Okay, end to end. That's another contribution. See, so what we did here, software based, and finally yes, convolutional neural network, and finally CRNN for actually recognition result. So this one not only recognition, even it will predict also. Okay, see, so convolution layer, recurrent layer, and transcription layer. So this is the input image, and this is the feature sequence, and finally this is for recognition, and of course output. So look at now, maybe yeah, what is the character? D is missing, but yes, road. You can predict the word road. Of course, this will not work for name of for names. Okay, your name is there, right? So this is no system will predict your name. Maybe yes, is okay, orb is okay, but not name of the person. Okay, this is the whole architecture. This is an end-to-end model. So just look at the architecture. So next, another problem. Okay, this is just simple results. Yeah, this is what occlusion I'm saying. Look at the tree. See, you're missing some characters here. So let us see this tree not only creates a problem for detection, not only for recognition, it creates even for detection also. So because of the tree, sometimes the feature whatever you extract will overlap with the obstacles. Okay, obstacles. Okay, next. This is another again. This also maybe you can say the person identification tattoo. The very new challenge here. So generative adversarial network for tattoo and scene text spotting. Look at now. This is again one more interesting challenge. So it is not just scene text detection recognition. So we are trying to add now tattoo. It's also kind of a text, but it is actually something similar to handwritten text because you people write, design. You design something, so by hand or maybe system, but it looks like a handwritten, not a normal text. Now, so look at the complexity of the problem. Look at the challenge here. So we are trying to our method should detect, recognize both tattoo and normal syntax. It is sporting. Sporting in the sense what? Yes, both. Sporting includes both detection and recognition. Okay, not just detection. Sporting involves both detection and recognition. Okay, spotting is very simple. Okay, what is the meaning of a spotting? Probably, I think when you ask your friend, "Where are you?" Yeah, how we can say? Well, yeah, you usually he tells us some landmark, right? Okay, I am here. That's what I'm spotting. You are trying to spot. We can understand the whole scenario or whole. Yeah, in text means what? Okay, just one word is enough to understand the whole page, or maybe whole para, or whole sentence. So there will be every sentence and every para will have some dominant keywords and important keywords. So if you are able to understand those words, then no need to, yeah, do something to understand the whole para. You can guess it. Oh, this para probably, yeah, describe something like that. So that is, of course, a sporting. Anyway, that's all document analysis. I don't want to explain what is the meaning of an sporting and what are the application of an sporting. That's not very important here. So what is very important? So now challenge is something like this. So we are including now tato text and scene text. This is the combination now. So how we can see our approach is Hilbert transform based generative adversarial network now. See here we brought an adversarial, that means a GAN. Why we brought a GAN here? Of course, what is the complexity of the tato? I think you know very well. Tato text detecting tato text is not so easy because whatever you write that will overlap with the background because the way the design, yes, even we cannot read anywhere the text, right? So when you write, what is that? Mehndi, not Mehndi, what do you call that one? Tattoo. Yeah, especially, yeah, I forgot. Yeah, when you write a tattoo, definitely yes, text will overlap with the design. So when text overlap with the design, how we can detect it? If we see, even our eyes may not see properly where is the text. Okay, we cannot read. We have to look at many times and close up way to read and text information. Then how algorithm can work? And it is handwritten. It is not printed. It is something like a handwritten. So definitely, yes, the background is there, decoration is there, and it is overlapping with the design also. And not only that, skin is also another problem. Okay, when you write this tattoo on the skin, not in a normal images. So skin definitely there will be a folding effect will be there. Okay, deformable effect will be there, and skin tone tone of the skin changes, right? So that means in black, white, skin color also changes. Yeah, it is. It's not so. And even the part of the body is also very important. Okay, tattoo on hand is different. Tattoo on, yeah, back is different. Leg is different. Okay, like this, So it's very complicated problem. It's a very complex problem. So our work is not just in a tattoo. Yes, whatever we design to detect in a tattoo, the same approach should work for even scene text also. That is what the whole work, and it's in this way it is a different now. Now, how we can solve the problem? Yes, for scene text, no problem. For tattoo is the problem here. So what we did here, of course, we cannot generate in so many samples here. To generate a samples, we brought in a GAN here because that is the main key characteristics of an important characteristic of an GAN is what? Okay, when you give input, automatically it will generate any samples which are similar to input. So since Tato, we don't have enough number of samples for Tato detection recognition. So we introduced a GAN to generate any samples here. So here GAN work behaves, work like, GAN, solves both the problems here, detection as well as the recognition. So in that way, we used, GAN architecture for detection recognition. Of course, Hilbert transform. This is something like this, So this is maybe you can say it is a Fourier transform only, just a different version of a Fourier transform here. So it will try to enhance the image now. So enhancement in the sense what? Enhancement you have to be careful here. If it is a low contrast, you should enhance it. If it is high contrast, you should not enhance it. That is what you need to understand here. If it is just enhancing, if it's already high quality, again if you enhance, what will happen? Again, then you will not get yeah, then there will be some problem. So if it is low contrast, yes, you can enhance it. That means you have to take a decision. Okay, now is it necessary to enhance now? Whether we can enhance now or not. So you need to take a decision. So every stage, yes, you need to check it whether we can enhance it or not. If it is a low contrast, you can enhance it. If it is high contrast, you should not enhance it. So that is where enhancement contributes here. So here what we do, we first enhance the image and then we use GAN to extract the features for detection and recognition. Okay, that's the whole work here. Look at now. So what is enhancement here? We are trying to extract the edge features here. That's all. Always, you have to look at any edge. Edges are very, very important. So you do whatever you do, somehow, directly, indirectly, you will try to extract edges only. No doubt in that. Okay. So generator now. Anyway, where generator is generated loss, and it is the loss to extract features, and finally discriminator. Generator, of course, GAN will have two things, right? Generator and discriminator. Generator generates samples, and discriminator, yeah, try to classify the things. So look at now, this is generator architecture. This is a discriminator architecture. So now we try to combine this one as an end-to-end model. Okay. So simple results. Look at now. It is not easy to solve this problem. This is really, of course, this is already not published under revision. Another problem now. So end-to-end model for multi-view syntax recognition. Multi-view. See, look at the problem now. So what is the syntax? See here, multi-view. We are focusing on multi-view syntax recognition. See, so far I discussed what single view. What do you mean single view? Okay, there is a single camera which captures one image. That's all. Now, same spot should be captured by multiple cameras, not one camera. So for every image, you'll have multiple views now, maybe 3, maybe 4. See, application is something like this. So assume that there is a spot now. So for the same spot, maybe supermarket or you go anywhere. So there will be multiple cameras will be there. So all multiple camera target the same spot now. So same spot captured by multiple camera, resulting multiple views, resulting in multiple views. So now look at the complexity now. Same spot, but you are capturing a different angle. Since you are capturing same spot in different angle, so you will have a different effects now. Not only different angle, different capacity of your camera, distance also. One is very close, one is not very close, another one is far, another in this angle. So this is where the problem. But one thing you should understand here, what is very important, common information. What is common? Because something should be common. Why? Because you are targeting all multiple cameras are targeting same spot. Something is common. So can we use this something common to solve the problem? Okay. So idea is this: when you have a multiple view, what happens? Assume that in one view, yes, there is one view provide good information. Another view does not give any good information. Another view yes provide some information. That means it is something when you have a multiple views. Yes, we can fuse the information. That means you extract something good, something good, something good, and finally fuse it. So this is the advantage of a multiple views. Of course, it is really challenging, not so easy. Okay. So again, it is end-to-end model. Let us just see the architecture, then we can understand. So now, so we propose, what is very important here. Again, here also we try to use a unit here. So unit architecture. So this is also network. So cycle consistency pairwise similarity. So that means, of course, as I mentioned earlier, so multiple views capture the same spot. Since multiple views of in the same spot, definitely we can expect something common. So what is that something common? So how we can expect something common? That is what we defined in a cycle consistency pairwise similarity in multiple views. So that means you'll try to compare all the views and finally you decide what is common here. Okay. Then, so of course text is a common. So definitely text components will extract and modified unit will segment. Okay. So similarity, based on the similarity, we'll extract what is the common. That means there is some reason. Now we got some reason, common reason. Now within that, so we'll try to use unit for text components reduction. Then, of course, Siamese architecture. We brought in Siamese architecture. So I think Siamese architecture is, you know very well, it's something like a parallel comparison. Okay, so that means something is same thing is going to two network here. You are just it's actually we use a Siamese network for comparison purpose. So if you want to know the similarity between the two things, yes, we can go for a Siamese architecture here. So, yeah, that's the thing. And finally, of course, in this approach, genetic algorithm also we used, and even NLP also we used here because the uh, genetic algorithm. So why genetic algorithm here? Because you are extracting so many things, from the multiple views now. So what genetic algorithm does here? Of course, you know very well that genetic algorithm extract a dominant one. Okay, so dominant one. So when you have too many things here, so we apply genetic algorithm to choose the best one. What is the best one here? The text is the best one here. Look at now. This is the CCPS. Okay, similarity measurement and detect a text reason. Okay, this is CCPS. Try to detect and text information for us. And then this one is architecture for text extraction. Okay, once you detect the text information, we'll try to, that means in a CCPS, try to extract the reason. Okay, from detection. Okay, it gives a detection part. Then extraction, we extract the extract using a DC unit. Okay, this is a unit. And then superimposed framework. This is actually SIAMIS work, superimposed framework. So what we do, something we get from U1, something you get from U2, something you get from U3, then finally you just fuse it. Okay. Once you fuse, then you will try to get fused information. That is something like combining, because some information is available in U1, some other information is available in U2, U3. So try to extract those information and finally you fuse it. Okay, and of course this is for recognition. So you feed this extracted result to ACE network, and then for recognition. Okay, this is end-to-end model. See, challenging different. Okay, shape. Okay, it's fine. Look at now what is happening now. CCPC, this is V1, this is the input now. So CCPC try to give important reason here, that means gives an text information here. Then we use DC unit for segmenting the reason now. This is the extraction result, and we use Siamese network to fuse to get a final result here. Then of course recognition. Okay, so this is the end-to-end model. What is end-to-end model here? I tell you. See, here end-to-end model is defined only for detection recognition, not with similarity. Okay, so that means CCP detection and extraction, and detection extraction maybe you can say it's a one step, and finally recognition is another step. So we try to define end-to-end model. So I've already explained what I mean by end-to-end model, how we can define end-to-end model. So that is done using detection and recognition. Okay, this is another yeah, this is another category. As I mentioned, I'll try to discuss in three kinds of work. One is handwritten, another one text reduction and recognition, another one personality traits. Okay, so new contrastive learning based model for estimating degree of multiple personality traits using social media post. Okay, this is a recent one. So of course, personality traits identification is not new problem for NLP people and NLP field. So, but NLP people use text as input for personality traits identification. But in our case, we don't use, don't we just don't use only sorry normal text. We try to use image information. So that means its idea is something like this. See, NLP people always take normal text. Okay, assume that you type and you upload text on the social media. You are typing some text. Okay, based on the text information, they try to predict what's the person right. Assume that and you are typing. Okay, you are in a totally different mode. Maybe you are in a depression mode. What kind of a text you type? So I will type when will you type and something like joyful, enjoy this one, laughing. You will not type because you're in the depression now. So definitely you will type all the words in some kind of sad words, which indicates sad and you are not happy, right? So that is the way NLP people solve this problem. So they try to use words as input, and finally the meaning of the word to decide what is his behavior, what is his typing, what is his uploading. That is all done. But nobody has done using images. So yeah, we people started thinking, why not? When you look at the face, when you look at your body language, and look at your action, easily we can get it. What is your personality traits? Looking at your eyes, easily we can say that you are confident or not. Looking at your face, you are yeah, you can guess it whether you are confident guy or you're a brave guy or you're a strong guy. Yeah, easily we can predict it, right? So that is what actually we did here. Of course, we use both content, that means an image content as well as the text information. So in this work we'll try to show not only text information, we should use even image information also. That means, yeah, if you use both information, yes, we'll get better results. That is what the whole approach here. Here you try to understand. So there is a word multiple personality traits. Yeah. This is interesting problem. So what I explained, it is just personality traits identification, but this is a multiple personality traits. See, in one image, let us say extraversion image. What is extraversion? It is something kind of joyful, okay, laughing, playing, dancing. Yes, there are things will be there, okay, in video or in one image. So when you look, assume that one single image will have, maybe multiple persons and different persons and different actions will be there. So when you see the person, assume that I'm looking at one person, definitely I will see one person writes, another guy will see another person in the image, then yes, there will be another person to trans. So like this, when the image will have too many persons and too many actions, multiple emotions, multiple expression, yeah, definitely you can expect a multiple personality types. So that's what actually we defined the problem here. So if one image, one personal traits, it is easy. No. In one image, multiple emotions, multiple expressions, yes, multiple personality traits. Okay, that is what in this work. So this is something challenging. In one image, there will be a different behavior. So you need to extract a different behavior. It's a degree. Okay, first one, maybe 90%. Okay, personal traits. This was percentage. So with percentage, okay, degree of percentage, the degree of another one, degree. Okay, which one is a dominant? Maybe yes, you can choose. If you want to choose this single percentage rights, yeah, you can choose a dominant one which gets an highest degree. Okay, that is the way we solve this problem. See, this is simple work. See, and okay, what is the approach we used? Contrastive learning based model. So, what do you mean by contrastive learning? This again, it's a new learning model. Of course, now we can see this is very common now. Contrastive learning. So, contrastive learning means, of course, this requires two things. Okay, so intra-class, inter-class. So, it will try to widen the difference between intra-class and intra. Widen means, of course, if it is intra-class, then you will try to bring to close, and if it is interclass, we'll try to widen the gap. Okay. So of course, so maybe I think the next diagram probably gives a clear explanation of a contrast to contrast learning. Now try to understand here. This is the input image. So face, we try to separate any face information, because without face you cannot see what is the personality traits. That is, we need a face and we need a action. We need a something. Face is most important feature, important information for personality traits and emotions, everything. Okay. Then text, whatever the text is available in the image, will take it. Okay. And finally, background. Okay, face is one part, text is another part, and the background, that means other than text and face, is another part. So we take in a three parts as a input here. Okay, then we'll try to fuse it. So to estimate a degree of personality traits, a degree of an openness, consciousness, and extroversion, agreeableness, and neuroticism. See, this is a contrast. Look at now. So what is happening? See, neurotism, neurotism. So these should attract each other. I mean, this is the same class. Sample of in the same class. Sample of in different classes. Okay, neurotism and extraversion. So there should be you should increase the gap now. That is what in a contrast learning here. Okay, in this way contrast learning works. This is the whole architecture now. See how we extract it and to finally solve the problem. This is okay, this is simple. But here you need to understand this one. Okay, we are trying to extract a recognition, that means a text. And for background, what we did actually, we just send in a background to Google Vision API. Automatically it gives in labels. So we take in annotations, that means labels. For background, actually, we take in labels. And yeah, this is annotations, that means in the foreground. We take okay, when you give in a face as input, you will get an annotations, and this is a recognition as a text. Okay, so that is the input now. Then finally, yes, we'll try to combine all these information using the weighted convolutional neural network, and finally we'll classify it. So okay, see, look at now, for this is the image. This is the percentage traits. Okay, there are five big percentage traits. That's a well-defined 5% traits. So openness for this image, actually openness. Ground truth is actually openness. Our method also, highlight openness percentage traits. Okay, yeah, this is the way. That means in one image we can expect 98%. Okay, percentage traits and openness, and maybe, yeah, ground truth. This is ground truth. 42, 59, 6%. Mm, uh, neuroticism makes 60%. Neuroticism, I don't know what indicates a neuroticism here. So openness is 97%. Consciousness is 42%. Extraversion 59%. Yeah, definitely extraversion means actually laughing, right? So smiling face indicates an extraversion. So like this, multiple personality can be extracted. Multiple degree of personality traits can be extracted in one image. Look at so many I discussed, right? I use a word multiple in different context. So that means I am trying to define always in a new problem. I don't take same problem. Usually I try to define a new problem. Of course, when you define, I believe when you define a new challenge, yes, we have to bring something new to solve the problem. That is where we are trying to justify in our contribution. One more work, maybe this will be the last one. So, a new visual question answering model for personal traits in social media images. See, I've already explained what is the problem with social media images. Okay. See, whenever we mention social media images, we should remember that. So, each social media image will have its own mechanism to store the data. So, that means compression. Okay. So, when the same image passing through different social media, then we can expect different quality variations in the image. Okay, this is the really challenging issue. Now, visual question answering model. So visual questioning, question answering in the sense what? This is actually, yeah, people introduce this one for computer vision. Introduced in computer vision, people introduced to answer user query. That means, see, when you look at the scene image, let us say scene image is there. So for you, it looks something beautiful. For another guy, it looks something different. Another guy, something different. So that means in one image, we can expect a multiple user interest. Okay, multiple user interest. Then how we can answer? So one guy is asking, okay, there is a cat. So I need to segment the cat information. Okay. So above the cat, there is something in a box. So I want to see the box, which is above, cat. Yeah, that's a question. You can ask anything. So by looking at the content, so can we answer is query? Can we answer is question? So that is what usual question answering concept. That is again it's a new concept and a new work. But of course, this is done in the computer vision. It's not a new for computer vision people. So what we did actually, see in the previous work I've already introduced a multiple degree of personality traits. What we did here, we just extended to visual question. That means we interpreted same thing as visual question answering. See, that means instead of saying in a multiple degree personality traits, what we did here, there is a question on this personality traits, or there's a question for this personality traits. One more question for another personality traits. One more question for another personality traits. That means we can expect a five questions for five personality traits. So we define this problem in different way now. Actually, solving problem is same, idea is same, concept is same. Only the change is interpreting the question in different way. So, because yeah, in computer vision, we have been seeing, okay, computer vision people are working on visual question answering. So we defined this one. Okay, personality traits question answering, something like that. Okay, that's an interesting topic we defined. Yeah, some motivation I've already explained. So what is the approach now? Look at again the same approach. So we don't change anything here. So sample image, okay, person detection, text recognition, content label. Okay, there is a question extra. Okay, this is actually combination of an NLP concept and computer image concept. So as always, you can see multimodal concept here because text is coming as a query. Okay, query gives an text information. So we need to understand the text information. Similarly, in the image also there will be text information. There will be image, actions will be there, face will be there. So we need to combine all the things. Okay. So what we did here, sample image. Okay, person detection. We try to first and extract the person and text also and content also. And finally, yes, person detection will send to transformer image encoder. This image encoder, this is actually text encoder because the recognition result is also text and this is the label is also text and the question is also text. Now, finally, we defined some now dynamic personality graph. That one define in the relationship, and finally, we'll decide DNN decides prediction. See, nothing changed. Only the change is question answering. Then a question. So you are getting a different questions here. So according to the question, you should answer it. Okay. If this question is related to this percentage traits, yes, you should give information about that percentage traits. So this is a simple approach. We're extracting text and image information, and we'll combine. This is a combination image encoder and text encoder. This is the combined matrix, and finally we define, yeah, this is a graph, and based on maybe cosine similarity, yeah, we use a cosine similarity, estimate the degree of similarity here, and the question which matches with the degree of similarity is the final answer. Okay, I think that's the thing. This is a simple result. Yeah, so question, what is the percent rights of the person in the image? Answer, that's our method. Ground truth is actually openness, our method. Okay, existing method, this one. Yeah, see, it's openness. He's open. Look at the face. Okay, and look at the text. Text also indicates it's open. Yeah, I think that's all. That's the last topic discussed. Yeah, yeah. As I mentioned in the beginning, so my focus is not machine learning things. So my focus is uh, oh, yeah, my focus is there are different challenges here. So how we can solve these challenges by proposing different deep learning concept. So what is the motivation to bring deep learning concept to solve the challenge? Yeah, yeah, that was whole uh, whole the target of my talk.